Cool. So is everyone happy with with this first exercise? Can I show the answer? Or do you guys want a little bit more time? Yeah, I'm gonna go ahead and show. Okay. So yeah, the first one is you just really needed to convert this left side into an expression and then simplify it. So it's just knowing to use the cos h and the sin h functions, and yeah, I guess how to use power. And then this is simplified even further. Let's see. Okay, yeah, and then I guess you do this for the other one as well. So if we do n times x and you get the same thing. Cool. Yeah, so everyone happy with that? We can go to the next exercise, which just asks define a polynomial with these roots and derive an expanded version of it. So I'll give you some, just do it the same way, just in a new notebook or something, and try and solve that. Do you guys still hear me? Do you? Give me some indication in Slack. Just if you're
Yes,
with
yes,
me.
all fine.
Okay, cool. All right. Thanks. Tsepo, on your question, yeah, that's fine. What you did there, you should just show that the other side of the equation is also equal to whatever that simplified expression gives. So on this side, but yeah, I mean that does seem fine. Okay, so is everyone, do you still want some more time with exercise 2? Or sure, can we go to the solution? I see someone has posted the solution in chat. But if the rest of you, okay, more time, yeah, that's fine. Yes, so to hide cells, I'm using Jupyter Lab, so I'm not sure if it's the same in your notebook, but it should be. I just here on the left, I can click and then it hides it. Yeah, that's how I do it. So that's useful if you have a lot of outputs that you don't want to show and you're using a Jupyter notebook as a presentation tool. Another useful thing for it as a presentation tool, which also I'm just show an example while wait if this works. A lot of the times, especially when you're maybe installing a package and it has a lot of outputs, you see this is quite, it's not nice to have to scroll through your old Jupyter notebook to get to the next cell. What you can do is when you right click on the cell, you can say enable or disable scrolling for outputs. And if you enable this, then the cell has a fixed width and its own scroll bar, which just makes it easier than, to also present things and navigate around your notebook. You just have to look for the two scroll bars. So that's also useful. Okay, how are we doing? Can I go to the solution? Is everyone ready? Or is there anyone that needs some more time? Seems like we're ready. Cool. So yeah, you define your polynomial, which is just giving the expression, and this means it has the three roots of 1, 2, 3, and then you can expand the polynomial, which does the multiplication for you, which is very nice. And then if you want to go the other way, you can just factor it back again. So yeah, very nice, because usually you have to do this in your head if you just have a piece of paper, but yeah, this makes it easy to go both ways. Nice. Okay. Then exercise 3 is more of a quick review rather than an exercise, but it's just showing how to work with complex numbers, which I think maybe you use we'll use in the second tutorial or in the second lecture. So yeah, as Francesco said, for complex numbers, you use the imaginary unit I. So just sp.I is I, which if you times it with itself, so it's defined as the number where it times with itself is -1, or the square of it. So it's the square root of -1. And then if you want to represent a general complex number, all complex numbers have a real and an imaginary part. And the imaginary part is represented as a multiple of this imaginary unit number, right? So this is a complex number, 4 plus 3i, and just the same way that you would write it down, it's you type it in code this way as well. And yeah, so the real part, there's a sp.re function, which returns the real part of your expression, which is just the complex number, and it's 4, and the imaginary part is 3. And then you can also get the conjugate of it, which is then 4 minus 3i. And then what you should be able to do is we have our complex number. Let's give this a name, C bar. So z times c bar is that. I wonder if you expand this. Yeah, so a complex number times its conjugate is the square root of radius, or it's a real number again, because what happens is it's the i's cancel out, so you basically get 4 squared plus 3 squared, which is 25, and then the norm of z, or the length, would be the square root of that 25. And then, so I think what we wanted to show here is we create another symbol. Oh, it's the Euler formula. So there's that famous formula in mathematics, which says that e to the ix is the same as I sine of x plus cosine of x. So yeah, I guess this is just showing that. Let's see, if we just take, so this is the exponential of I times x, right? Which is just e to the x. But if you expand this with, and I guess this argument for complex true, you get that it's the same as I sine of x plus the cosine of x. Which is quite a nice result, and a very useful thing in mathematics. But yeah, it shows that SymPy also knows of it. And I guess the more general version would be, usually it's given like this, e to the x, and the full, you usually have a variable r here as well, to give the length of the complex number. But yeah, anyway, that's not important now. So yeah, that's just a quick review on complex numbers. And the next exercise has to do with integration, which we'll do in the, I think your second lecture, if I'm correct, as we'll do a bit of calculus. So we'll leave that for the second tutorial. And that's then all the exercises for this tutorial. And maybe one more thing that we can try and do. Let's see, where's this now? Is yeah, so I'm going to give you one more exercise, but it's not in the notebook. It's just but you can see it here on the screen. So you have the binomial theorem, right? Which, if you have your two symbols, x and y, and you want to take any power of it, maybe you have a variable n. Okay, so x plus y to the power of 5 is, well, we can just see that it looks like this. And if you know the coefficients are all numbers from Pascal's triangle. So it's just, there's a whole nice binomial theorem, but there's a formula for this to get each coefficient. And you can see a nice pattern because it's x to the 5, x4, y. So you see your x's goes from 5, 4, 3, 2, 1, 0, and your y's goes from 5, 4, 3, 2, 1, 0, and it all has, it has this form. So I'm going to show you the, okay, I'll answer this question now. So just as a, I guess, an additional exercise, I'm going to show you the formula for the binomial expansion, and then I want you to get this expression, but without getting it in this form. So use a for loop that goes from 0 to 5, and keep appending your expression with the correct coefficient, if that makes sense. So I showed you a quick example earlier how we can build an expression with a for loop. So I just want to get that quickly. And then I'll answer the questions. Okay, it's not here right now. So just to help you out a bit, what I'm wanting is just some kind of thing that starts like this. You start with your expression of 0, and you go with maybe a k in range 0, to like your n that you define, and you step in 1, and then you keep on updating this expression. So you're going to go from here to here, basically, and try and get this. And the formula is, I'll show that now. It's this this one. It looks like this. So you'll just have to figure out how to do this in combination k. So I mean, your for loop is your summation, and see if you can find in SymPy how to get to basically get the choose function, or maybe it's also binomial expansion, and then in each loop just create the expression for this formula with a for loop instead of just using the dot expand. So basically you're coding the dot expand function for this expression for SymPy. Kind of like as an additional exercise, see if you can do that. This is called the binomial formula, so you can Google that to see the what the formula looks like, and the expression, and see what you can use from SymPy to make it look like this for a given n, and without using this dot expand function, basically. And then for extra credit, you can get it in this form with SymPy. I think that would be possible as well. Anyway, so you guys can try that out. And then if you have any other questions on the things we covered, you can just ask them in the Slack chat, and then we have like 30 minutes and I can answer that, and maybe talk about other things that you might want to know about. So on the, can I please show how to draw the graphs? Yeah, I'll show that now because we figured that out just now. And so there's just a question on the complex numbers. Yeah, Andrew answered it. Yeah, it just returns the real component or the imaginary component of the number. Okay, so let's go to that plotting again. While you guys try the extra exercise. So for plotting, I just took the code now from that Andrew shared, but it's very much the same. It's just this. So you have this from SymPy, you have this plotting function from SymPy.plotting, and we're gonna just define our symbol, and we create our function or equation, y equals x squared, and then you have a plot. You just call the plot function, you give it the expression. And this show probably just says whether it should show it or not. And then because now you can interact with this with the variable, and then you can really just show. So this is, I should run this probably again. Okay, this is not y, this is y. Okay, and there's your parabola, y equals x squared. And if we now do plus x, it should update. I think it tilted it a little bit. Do something bigger. Yeah, there we go. And yeah, so that you can create an expression like this, and it will plot it. So it's pretty simple. It's pretty straightforward. There's y equals x cubed. Yeah, so that's the basic use. I haven't used it that much, so I don't have that much I can say about it. I think this one, oh, it's you can append plots. So maybe we have another another function, which is just a straight line. Get our second symbol. I don't need that. So just y2, and then all I need to say is p1 dot append, I think y2, and that is maybe p2. You need to make it a plot as well. Okay, let's see. So you have another expression, so you create another plot. And we're also not going to show it now. So our P2 plot, which is just a straight line. Oops. Is this y equals to a straight line? If we move it up a little bit, just add 5 to every output. So it just moves it up 5 units. And then if we want to show plots, it seems, we can just take our first plot and append the second plot, which is pretty neat. And then just show it the first plot. Or not. Okay. Seems you have to append. So the P2 is a list of a bunch of objects, and the first object is the plot information. So it just needs to be subscript here. And then, yeah, there's our y equals 2x, and because we have such a large range for this one, it's not showing as nice, but you get the idea. The y range is just way too big here, but you get the idea. Okay, so that's drawing the graphs. And then let's just see, there's another question. So these Idris, your question. So that might just be these things. So that might just be the version of Jupyter that you're using. So like I said, I'm not using Anaconda, so I'm not exactly sure what your and the others' environment looks like. And my version of Jupyter, so I use Jupyter Lab, which also just is uses Jupyter notebooks, but it might be a different version where they added these this layover for the cells. Usually, it's here on, some of these are on the top, or I think with edit you can like do all these things, move a cell up or down. So like move cell up, move cell down, which is those, or add new cell bottom or below. Which, yeah, but yeah, so I'm not exactly sure. That might be your version. So you can try and update your Jupyter notebook or something like that. But again, I'm not sure how to do that with Anaconda. There's probably an option close somewhere. So yeah. Yes, so SymPy can be used for data science. On your question, Nyasha, and but it can be used for a lot of other things as well. So I mean, you can, if you're doing a simple model like linear regression, you can nicely represent we can represent it with matrices, but also just a whole equation for your linear model with its coefficients, because linear regression is something like x0 or beta 0 plus beta 1 x1 plus beta 2 x2. You can imagine how you can nicely create that with SymPy, and then add and you add things like regularization terms, or you can just represent your equation very nicely and explore what else you can do it for a machine to then learn or do gradient descent. I mean, yeah, you can get the derivatives of your model as well. So you can use it for data science, but you can use it for physics or anything else, really. Cool. Let me know if you guys have any more questions about the specific question that I asked, or any other questions. Otherwise, I'm assuming you're all trying to get this expression without using expand. Yeah, so Idris, I see the problem that you're having. So I'm not sure, because it depends on your environment. Yeah, the only things I can think of that you can try is, if this, even because that's what, there's nothing in the cell and it's just running. So if it is open in Jupyter Notebook or anything, and you've run it, and like the star just stays there, you can try restarting or refreshing the page, if it's in Jupyter Notebook in Google Chrome or what browser you use. And the other thing that you can do is try and restart the kernel, which is, there's this restart kernel option, because that has to do with the underlying Python that it tries to run. And then another thing you can try to play with is, so for me, I have this, I can select the kernel. You're on the top right. So you can just see, maybe you have no kernel or something else. Just see if you have a Python 3 or something, or if there's other things here under preferred kernels or other kernels, try and use that. But that's all that I can think of for now. But yeah, refreshing everything might help. And just make sure you have the right things installed. Cool. I see we have one answer. Do the others, do you guys want more time, or have you all done it? Okay, so can I get to the answer? Isn't no one's saying they want more time? Yeah. So, yeah. Yeah, I think Mukhtar gave the right answer there. You can just use the binomial function, which does the n choose k or n choose I to get the expression. This gives you a nice idea. I mean, maybe an idea of how this would look in the background, although it's way more complicated than that. But that you can build an expression with a loop. So if you have a complicated pipeline or some interesting programmatic things that you're doing, especially if you have functions that maybe even returns SymPy symbols or other things, you can get very dynamic with it very quickly. So what this does is just, yeah, it appends the expression per term, and each term gets an xy term with, and this ni is basically just all the ways that you can choose 5 items or I items from n items where ordering doesn't matter. So it's just the normal binomial. So choosing 4 things from a set of, or 2 things from a set of 4 things, you can do in 6 ways where order doesn't matter. And you can build it just element-wise up like this. So yeah, so your answer is correct, Mukhtar. Then yeah, that's, I think, all the exercises for this tutorial. Do you guys have any other things that you might want to know or want me to talk about, since we still have some time left? Any other questions you can think of, or applications? So Masego asks, how can we express an angle in Python? Well, it depends exactly on like how you want to use that angle, right? But you can, if you want a symbol for an angle like theta, there is the SymPy.symbols theta or phi, which is just the Greek. This is just getting the Greek symbol for it. And then you can work with that with like the other SymPy functions. So is that what you wanted to know, or is there more specific use? Yeah, and if you do sine and yeah, any trigonometric function, the assumption is gonna be that you're working units or radians as units. So we can do something like pi. So this is since you're working in radians, you can have pi as a variable or something. So the sine of 2 pi is 0, and the sine of, or the cosine of 2 pi is 1, right? And if we can plot this, get that plotting functions out. Yeah. So let's just say our y is the 2, well, 2 pi x might make a lot of sense. We'll probably just want x, see what that does. So there's our cosine function. And then can maybe do something like but already this you can see this is going to be in I think gradients. But yeah, so you'll work with it basically that way. So any other questions? Yeah, if there's no other questions, we can end a bit earlier. I see here Amula sp.i output I. Yeah, so that's just the imaginary unit, right? So this I, which would be probably the same as a square root, I think, of -1. Yeah, so these are equivalent. This is what it means. It's the square root of -1. These are the same. So that's just your imaginary unit to represent imaginary numbers. And yeah, this would be this is also a complex number, but its real part is 0, and now its real part is 5, right? So that's what the I means there. Do you want to display it as the square root of -1? I'm not sure, because I think it maybe, because this will probably also give I. Yeah, I don't know. Maybe if you expand it or factor it, I don't think. But yeah, usually people use just I because the square root of -1 is a bit more like not as nice to write out. But maybe if we do, sorry. I'm not sure. Yeah, I'm not exactly sure. If you want to do it in just Markdown, you can do that. I think it would just be the square root of -1, which would be like that. But with SymPy, for it, the simplest version is I. My help about version, sure. So this is the sys version. I'm using Python 3.8.1, and is this what you want to see? I'm using JupyterLab 3.5.2. Yeah. So that's what I'm working on. Cool. Yeah, so the you guys did Linux, right? So what instead of using, I'm not a big fan of Anaconda. How I work in, let me just show you the way that I use Jupyter, right? Is just in the terminal, I'll have an environment. This might not be too much detail, but in some virtual environment, you can just install Jupyter Lab, right? And I think you might need IPyKernel as well, something like that. So pip install that, and then all you do is you just call Jupyter Lab in the terminal, and then, well, it's not installed here. But yeah, if it's installed, then this will work, and that's how I got mine here. So you can just in some environment pip install Jupyter Lab, and I think IPyKernel, and then you should be able to just run Jupyter Lab, and it should just open it up in a browser. Okay, any other questions? Okay, maybe we can then go take a small break for the next session. But yeah.